Hello again, and welcome to Chapter 6. We have finished learning all those integration methods that you studied in Chapter 5, which leaves us with some odds and ends to which we must attend. First on the agenda are a couple of geometric applications, arc length and surface area. We will begin with arc length, and our problem is this. Suppose we have the graph of a function y equals f of x. If we pick 2 points in the function's domain, a and b, and look at the points corresponding to them on the graph, consider the part of the graph that stretches between those 2 points. How long is it? That is the question we want to answer. Well, in pretty short order, we are going to come up with a recipe for it. But let me state at the outset, your job is not to memorize that recipe. Your job, the whole reason we are doing this section, is so you can understand the process by which we get that recipe. If you understand that line of thought, then you are really learning calculus. If you just memorize a formula, it serves no purpose whatsoever beyond passing an exam. But don't forget, you are taking those exams. Nay, you are taking calculus itself for the purpose of learning how to think in terms of calculus, not just to memorize things. So anyway, let's do some thinking. What you are studying is, of course, the calculus of infinitesimals. Not surprisingly, it is infinitesimals that we will invoke to figure out how to compute arc lengths. And we need to reach back into Chapter 4 to help us understand how infinitesimal thinking can help us determine arc lengths in the first place. So here's the idea. We understand how to cope with length when it is along a straight line. I mean, what's the length of this line segment? Well, if you can tell me the coordinates of its endpoints, I can just use the distance formula. Or if I don't remember that, I can just draw a triangle and use the Pythagorean theorem, which is where the distance formula comes from anyway. The difficulty up here is that we are not dealing with a line segment. We are dealing with a curve. Well, the general spirit of integral calculus is to take something complicated and curvy and chop it up into infinitely many infinitesimal bits, each of which is simple enough to understand. So we essentially disintegrate the complicated stuff, analyze it in its simple form, and then reintegrate those pieces into a whole with an integral, of course. So how does that work here? Well, go back to first principles from Calculus 1. The key geometric insight that underpins all of calculus is that locally, meaning on an infinitesimal scale, curves are straight. Yes, with the usual caveats about corners and things like that. But this is the key insight that drives it all. For example, if I just take some typical point x in this interval from a to b and go up to the curve there, well, if I imagine a little infinitesimal neighborhood of that point on the graph. Obviously, I can't draw something infinitesimally small, so you have to use your imagination. But anyway, imagine this infinitesimal neighborhood and put it under an infinitesimal microscope. Well, on this infinitesimal scale, we see that the curve is, of course, straight. Well, this is great because, as we said before, we know how to deal with length when we're dealing with line segments. So down on this infinitesimal scale, let's cut off an infinitesimal bit of arc length. And because it is a little bit of length, I am going to call it dl. L, of course, for length, and the d tells us that we've got just an infinitesimal bit of length. Okay, now how is this going to help us? Well, this little bit of arc length we could think about as being generated by a little change in x and a little change in y, which of course I'll call dx and dy. And in our quest to come up with the length of the original curve, essentially what we want to do is get a useful expression for dl, an infinitesimal bit of arc length, and integrate, add them all up. Mind you, this equation here should really be understood in a kind of impressionistic sense, because what exactly does this mean on the right-hand side? Integrating L from where to where? Well, when L is what? To where L is, what would that even mean? I mean, what we really want to do is add up all those dLs as x runs from A to where x runs to B. But what does that even mean? I mean, my boundaries should really match the variable I'm integrating with respect to. I mean, for that to make sense, what we really need to do is somehow rewrite dl in terms of dx. Write it so that we have dl is something or other times dx, and then we'll be integrating as x runs from A to b, which is what we actually want. Okay, so how are we going to do that? Well, in the book, I explain carefully how to do that, and then I give you a quick and dirty way to understand it as well. But here I am just going to give you the quick and dirty way. What I show you is not going to be the last word in rigor, but it will get you where we want to go very intuitively. And if you have further questions, of course, you should read the section in the book. So, the quick and dirty way to come up with dl, the infinitesimal element of arc length. Well, we're staring right at it, a right triangle. So, of course, Pythagoras should come to mind. And Pythagoras immediately tells you that dl is the square root of dx squared plus dy squared. Okay, it's a good start, but our whole goal here is to write dl in such a form that it ends with a dx. That's the only way we are going to be able to integrate as x runs from a to where x is b. And this thing just does not end in dx. Whatever are we to do? Well, you know what to do. It's the same thing we always do in situations like this. It's the old multiply by 1 trick. I'm perfectly free to stick a dx in there as long as I divide by dx as well, because then the net effect is just multiplying by 1, which doesn't change anything. We have changed our expression's form without actually changing its content. Anyway, let's clean this up further. We have a 1 over dx. Well, we can stuff that inside of this radical, of course, if we square it, which gives us this, which can be simplified further by breaking the stuff under the radical into 2 fractions, like this. But of course, dx squared over dx squared is 1, and dy squared over dx squared is the square of dy over dx. Hey, that's really nice, because now we have dl is equal to something times dx. And the something, better still, is something that we can compute, because this ratio dy dx is, of course, just the derivative. So if we know our function y equals f of x, we can compute dy dx. So we can take all this stuff, carry it down here, it goes where we had dl before, and now we can just say we're integrating this junk as x runs from a to b. And there is your promised recipe for arc length. Now let me reiterate one last time. Don't be a dope. Don't just say, oh great, arc length, I just memorized this integral, and then whenever I have a question on a test, find the length of the graph of y equals f of x between x equals a and x equals b. I just stick it in this formula and I'm done. I mean, yes, that will get you where you want to go, but understand where it comes from. If you understand where it comes from and you just end up memorizing it by accident, by all means, that's great. But if you just memorize it and you can't explain where it actually came from, you haven't learned anything. And the goal should be to learn to think in terms of calculus. All right, I'll get off the soapbox. Well, one last thing. The only thing you really should certainly have burned deep into your memory is this picture. The idea that any curve is locally straight, because that's central to all of calculus. And so if I'm looking for arc length, I break the curve up into a chain of little infinitesimal straight lines, and I can figure everything out from this one little infinitesimal triangle, which I've sometimes seen called the differential triangle, which is a catchy name. It makes you think of the Bermuda Triangle or something. And if you understand that much, and you have forgotten this thing, the thing that you actually integrate to get arc length, you can recover it in 2 seconds. And that is a useful skill, not just for if you need to recover this thing, because there are many variations on this, some of which you will see in the next course when we are working with parametric curves that are not the graph of a function in an ordinary sense, and we want to find an arc length there. If you understand this picture and how that gives you the infinitesimal element of arc length, you'll be able to do the exact same thing here. You won't have anything new to memorize. Whereas if you just memorize this for some reason, you'll have a whole new thing to memorize, and it'll be so close to this that you might screw it up and forget which is which. Anyway, let's do an example. Set up an integral for the arc length of a circle of radius r. Then actually compute the integral to verify that the circumference of the circle is 2 pi r. Now on one level this is a silly problem because you know the circumference is 2 pi r. That follows immediately from the definition of pi itself. But this is a nice example to do because at the end of all our reasoning and computing, we should end up with something with which we are already familiar, and that will be a comfort and give us encouragement that we really do understand this novel path to a familiar result. Okay, our solution. Let's start with a circle of radius r, which I'm going to center at the origin to make everything easy. You might detect a problem already. You might say, hey, wait a second. We discussed how to find the arc length of the graph of a function. This is not the graph of a function, now is it? Because for every value of x, there are 2 values of y. Oh, but that's okay. We're lucky. We can use the fact that the circle is such a wonderfully symmetric object. We can just concentrate on the top half of the circle, which is the graph of a function, find its arc length, and then double it to get the circumference of the whole circle. In fact, we can do even better. Let's find the arc length of just a quarter of the circle, the stuff in the first quadrant. That's going to be even nicer for our computations because both coordinates are positive throughout the first quadrant. Oh, we're already off to a good start. But whether we use a quarter or a half, we do need to think of this as the graph of a function. So take this stuff in the first quadrant. It is the graph of a function. Which function? Well, of course, it's going to be y equals the square root of r squared minus x squared. That's something you should know. If you forgot it, of course, you could just remember that the full circle is the graph of the equation x squared plus y squared is r squared. Solve for y, and you get y is plus or minus this junk. And of course, we get the plus because we have the ones in the top half. The y coordinates are always positive. Okay, anyway, we'll need that in a bit, and we want to find the arc length of that portion of the circle. How are we going to do it? Now, I'm pretending here we don't really remember. How am I going to get it? Well, of course, if I remember the basic idea, I can reconstruct it very rapidly. I can say, well, I remember the basic idea, of course. We get this whole length by chopping it up into infinitely many infinitesimal bits, because each bit, like say this typical one, which I'll call dl, is straight because curves are locally straight. Well, how does that help me? Well, let's think infinitesimally. On an infinitesimal scale, that little neighborhood shows us that infinitesimal bit, dl, as the hypotenuse of a right triangle, whose legs are dx and dy. And we are ultimately going to be integrating dl, so I need an expression for it. How do I get one? Well, the picture is showing me. Just think about Pythagoras, who instantly tells me that dl is going to be equal to dx squared plus dy squared under a square root. Hey, but wait a second. Ultimately, I'm going to be integrating with respect to x, as x runs from 0 to where x is r. So this isn't going to be much use to me as it stands. I need to be able to rewrite dl so that it ends with a dx. Am I out of luck because I don't have a dx here? Of course not. We can multiply by dx as long as we divide by it as well. But this 1 over dx can be stuffed into the radical if we square it, giving us this stuff, which of course simplifies immediately into 1 plus the square of dy dx. Oh yeah, that's right. That's what we found a few minutes ago. Good to see it again. Anyway, this is the kind of thing I will integrate to add up all those little infinitesimal bits of arc length to get the entire arc length. Hey, that's great. I'm pretty much ready to set up my integral, where I integrate all those dl's. Oh, but you know what? Before I do that, I realize, in looking at this thing that I just came up with, that I'm going to need dy dx. So let's go ahead and get that. All right, well, I already have y as a function of x right here. So dy dx, well, let's see. I just take the derivative. That's going to be 1 over 2 times the stuff in the radical, but I need the chain rule. Derivative of the stuff inside the radical is minus 2x. Let's cancel those minus 2's and we have our derivative. All right, now let's set up our integral. Well, the length of the full circle, i.e. its circumference, we said is going to be 4 times the length of that blue arc in one quadrant. And to get the length of that arc, that graph of this function, we are going to disintegrate it into infinitesimal bits, each of length dl, and then add them all back up, reintegrate them. So overall, that length is going to be the integral, the infinite sum of all of those infinitesimals of the form dl. Now, I can't say integrate as L goes from something to something else. As I described it earlier, this is a kind of impressionistic notation, but that's okay as a quick bridge to get us to something we can actually compute, because we know now that dl can be expressed in terms of dx. Just import that stuff here. We've got the square root of 1 plus, well, let's see, the square of dy dx. Well, here's dy dx. So when I square that, I'm going to get x squared over r squared minus x squared. And don't forget, of course, the dx. The whole point was to get dx out there so we could integrate with respect to x. So we're going to add all these things up, all our little bits of arc length, starting when x is 0, right here, and stopping when x is r. That's when we reach the end of our circle. This is good. We have now successfully set up an integral for the arc length of our circle. So the first part of this is done. And now we just need to compute that integral and verify that everything works out nicely. But first, pause here. If you understand everything we've done up to this point, you've learned everything new we have done up to this point, because that's all the arc length. The rest is just cranking out an integral. Well, shall we proceed? Let's go ahead and do it. You should quickly realize that the stuff under the radical here simplifies very nicely. If you put everything over a common denominator, you end up with r squared minus x squared downstairs, of course, but upstairs you will get plain old r squared. Oh, well, that's good. We've got a factor of r squared under the radical, which means I could pull that through and it'll just become r. In fact, I can pull the r through the integral, and I'll end up with 4r, because remember, r is just a constant. It's the radius of this circle. 4r times the integral of the square root of 1 over the quantity r squared minus x squared, as x runs from 0 to r. And you know what? We can simplify that even further, because the square root of a quotient is the quotient of the square roots. So this is the square root of 1 over the square root of the stuff downstairs, which is just 1 over the square root of the stuff downstairs. This doesn't look too bad. How can we integrate this function? You might think, ooh, would a trig substitution work here? Maybe so, but there's a quicker way. What does this integrand remind you of? It should remind you a little bit of 1 over the square root of 1 minus x squared. Ooh, that would have been nice, because if that r squared had been a 1, we would recognize that this thing is just the derivative of arc sine. So you might wonder, I wonder if I could do like a kind of guess and adjust to come up with this. That should work. And to put it in an even nicer form, let's force the issue and really make this thing be a 1 instead of an r squared. How are we going to do that? Well, let's just factor an r squared out of each term under the radical, leaving me with r squared times 1, that's what I want there, minus x over r squared under the radical. That's not so bad, because the square root of a product is the product of the square roots, so that means I could write this stuff as plain old r times the square root of 1 minus the square of the quantity x over r. Hey, that's pretty nice, because now I have this constant factor of r downstairs, which I could pull through the integral sign. And when I do that, I'll be left with just 4 times the integral that's left over. And now this thing looks a hell of a lot like the derivative of arc sine. The only difference is I have an x over r where I would normally have an x. So now I'm really set up for what should be a pretty simple guess and adjust integration. An antiderivative of this stuff should be something like arc sine of x over r. But is it that exactly? Let's see. Well, what would happen if I took the derivative of that? Well, if I took the derivative of that, of course, I would get first this stuff. Oh, but then I need the chain rule. The derivative of the inner function would give me another 1 over r. That's not quite what I have here. Oh, but I know how to take care of that pesky 1 over r. Just stick another r in here. That way, when I take the derivative of all this, the r just sits there like that, and then the derivative of the arc sine part gives me all this other stuff. The r's cancel out, and I actually get what I was aiming at. Okay, good. So this really is an antiderivative of my integrand. Excellent. And we have our bracket notation set up for the fundamental theorem of calculus. We will need to evaluate where x is 0 and where x is r and subtract the corresponding values. Oh, we know that r's can be pulled through the bracket notation, so let's go ahead and do that. All right, now evaluating the bracket. When I pop r in here, I get arc sine of 1, and when I pop 0 in for x, of course I get arc sine of 0. Now you know your trigonometry, don't you? Sure you do. But for somebody else's sake, a quick reminder. Arc sine's range runs from minus pi over 2 to pi over 2, because in that range you get every possible value of sine, from minus 1 all the way up to 1. Okay, anyway, so arc sine of 1 is the angle in that range whose sine is 1. What's that going to be? Obviously, that is pi over 2. So we'll pop that in there. What about arc sine 0? That's the angle in this range whose sine is 0. What's that? Well, of course, that is 0 itself. So we have pi minus 2 minus 0. Do the arithmetic, and this comes out to 2 pi r as we knew already. So no surprises, and yes, this technique really does work. You will find another worked out example in the book, and of course several exercises as well. I should point out before we leave arc length that the integrals we come up with when we compute arc length, because they end up with square roots in them on account of this fundamental formula right here, they're often very hard, even impossible, to integrate in elementary terms. Nonetheless, it is valuable to be able to take a curve and come up with an integral expression for the arc length, even if you can't evaluate it exactly using the fundamental theorem of calculus. You can use numerical methods to get an approximation for the value of such an integral, and we'll talk about one way to do that at least when we reach the section on Riemann sums later in chapter 6. And who knows, maybe we'll revisit this material on arc length and surface area then, because the surface areas we'll be looking at as well. Often we will be able to set up an integral, but unable to actually compute it exactly through the fundamental theorem, because no elementary antiderivative exists. But that lies in the future. Arc length has had its day in court, and now we will proceed to surface area, at least in a certain special case, namely the surface area of a surface of revolution. Now, what on earth does that mean? The answer is very simple. If we start with the graph of some function over some interval, and then we revolve the entire graph around one of the axes, let's use the horizontal axis, we end up generating a surface. That is our so-called surface of revolution. It turns out that it's pretty easy to write down an integral that represents the surface area of such a surface of revolution. And as with arc length, as with so much in this subject, the important thing here is the idea, the process by which we come up with the thing. It's a great example of thinking infinitesimally. So be sure you understand the argument that leads to the result, not just the result, which isn't all that important in and of itself, to be honest. All right, how are we going to come up with the surface area of such a thing? Oh, and by the way, I'm thinking of this as a surface that you could stick your arm in one side and it would come out the other side. Think of it as hollow. All we really care about is the lateral surface area, the stuff that goes around the sides. I mean, the bases of it. This stuff over here and this stuff over here, those are just disks, so of course we know how to find the areas of those things. It's all this stuff in here that we're not so sure about. So how are we going to do that? Well, once again, we're going to base everything on that fundamental idea that underlies calculus. Locally, curves are straight. So I can think of the original graph that I started with, the graph of y equals f of x, as being not just a curve, but a infinite chain of infinitesimally small straight line segments. As with arc length, I'm imagining chopping this thing up into infinitesimal bits, each one of which is straight. In fact, at a typical value of x, we have a little infinitesimal bit of arc length, dl, which again you could imagine blowing up in our infinitesimal microscope. But let's not have that on our picture. The important thing is that when we generate our surface of revolution by revolving this blue curve around the x-axis, think about what happens to this one little infinitesimal bit of arc length, this one infinitesimal bit of the curve, and therefore straight bit of the curve. It sweeps out its own little surface of revolution, a much simpler surface of revolution than the big one we're working with. In fact, if we extract it from this picture and put it on its side, we get a better feel for what it looks like. It's simpler than the original surface of revolution because this one was generated by something straight. In fact, you can imagine this generator sweeping out in all of the various positions it occupies as it goes around this little ribbon. I'm not going to push my luck by trying to draw it back here as well. Moreover, to get a feel for what this thing really is, imagine extending all of those lines, all those positions the generator occupied in all of its positions, and what would we end up with? I think you can see. They would all meet in a point so that we would get this cone, which means that our little infinitesimal ribbon here is like a cone with its top chopped off, or we might call it a truncated cone. There's actually another term for a truncated cone that is commonly used in this setting. It's also called a conical frustum, which I presume is a cognate of frustrate, which is sort of funny. It makes it sound like this little thing is frustrated that it can't grow into the cone that it ought to be. Well, be that as it may, the important thing we have observed here is that our little infinitesimal line segment generates a conical frustum, or truncated cone, which means that if we are able to figure out the surface area, the lateral surface area of a conical frustum, then we should be able to get the surface area of this entire surface of revolution, because we take the surface of revolution, disintegrate it into infinitesimally thin conical frusta, analyze those, and if we can successfully come up with the area of a typical one of those at any old value x, then we just integrate that thing, and that will give us the area of the entire surface of revolution. So it's the old story. Chop up into infinitesimal pieces, analyze the pieces, and then sum up the pieces with an integral to recover the original and answer the original question, namely, what is the lateral surface area of such a thing? Okay, so if you understand that much, you are halfway there already. But there's one important detail. How do we find the surface area of a conical frustum? So let's talk about conical frusta in general. Any conical frustum is, of course, a surface of revolution because it can be generated by this line segment indicated on the picture. We just revolve it around the central axis and we get the whole frustum. Now, it turns out that the lateral surface area of a conical frustum is a product of two things having to do with the generator. The surface area we seek turns out to be the product of the length of its generator. This length is also sometimes called the slant height of the frustum, and the distance traveled by the generator's midpoint, which I'll indicate with a little red dot. By distance traveled, I mean the circumference of the circle that the midpoint traces out as the generator revolves around the axis. Now, this interesting little result is not that hard to prove, and the proof is, in fact, interesting, but it takes some work to do it, and there is only so long I want this video to be. In the book, I have a sequence of exercises in this section that leads you to the proof of this geometric fact. For the rest of this video, though, I'm just going to take it for granted under the assumption that you're going to do that exercise and prove it yourself. We are going to use this result, though, to come up with an expression for the lateral surface area of one of these little infinitesimally thin conical frusta that we can then integrate, sum up all the little infinitesimal bits to get the surface area of the entire surface of revolution. So let's think about how that would work in the general picture like this, and then we will do a concrete example afterwards. And I'm going to need to do a little housekeeping to give myself some space. Okay, that should work. So let's reiterate the original problem. I've got the graph of some function, y equals f of x. I revolve it around the x-axis, thereby generating this surface of revolution. We want to come up with an integral that represents the surface area of that surface of revolution. We have all the pieces in play now. We think of the curve as consisting of infinitely many, infinitesimally tiny straight line segments, each of which, say this one right here, with length dl, generates an infinitesimally thin conical frustum. So we want to figure out the surface area of that thing, and then we will add all of them up with an integral. So the surface area of a typical infinitesimally thin conical frustum at x, in other words, this guy right here, is, well, let's see, it's a conical frustum. We know how to find the lateral surface area of such a thing. That's easy. It's the length of its generator times the distance traveled by the generator's midpoint. And this is the kind of thing you should memorize because it's very memorable. It's not just a formula. You can feel the thing, in a sense. You got this little point traveling a certain distance, multiply that distance by that length, and bang, you've got the surface area. Okay, so what is it here? Well, it's the length of the generator. That, of course, is dl times the distance traveled by the generator's midpoint. Well, let's think about that one a little bit. This little infinitesimal line segment, this is centered above the point x. So the midpoint of that thing is directly above x. Now, how far does it travel when it rotates around the x-axis? Well, what's it doing? As it rotates around, it stays the same distance from the axis. That's what it means to revolve around it, of course. I mean, like in the bigger case over here that I could see, we have the axis of symmetry, and the midpoint travels around it on a circle. How far does it travel? Well, it's the circumference of that circle. What's the circumference of that circle? Well, everybody knows that. It's 2 pi times the radius, whatever that might be. Okay, we'll bring that back over here. Here we have the midpoint of that infinitesimal line segment. It travels in a circle. So what's the circumference of the circle it travels on? Is 2 pi times its radius. So the distance traveled by the midpoint's generator is 2 pi times something. What is that radius? Well, that is staring you in the face. It's the distance from the x-axis up to that curve at x. In other words, it's the y-coordinate of that point. Well, what's that y-coordinate? Well, of course, it lies on the graph of y equals f of x. So the y-coordinate is f of x. That is the radius of the circle that the point travels around. So its circumference is 2 pi times its radius, which is f of x. Hey, now we're in business. But let's back up a second and remind ourselves where we are. What we've just shown is that the surface area of one of these typical infinitesimally thin conical frusta, into which we have chopped our surface of revolution, is dl times 2 pi f of x. Does that help us? Well, we want to integrate this sort of thing. Ultimately, we want to be doing an integral from where x is a to where x is b. So I don't want my expression to end in dl. I want it to end in dx. But you know what? That's easy, because I already know how to get dl in terms of dx. We did it while we were learning about arc length. Let's rewrite this thing, and I'll put the infinitesimal bit at the end. It's 2 pi f of x dl, but we found that thing doing our argument with the differential triangle, which I repeated twice. I'm not going to repeat it a third time. By now, you may have already accidentally memorized it. You should be able to explain where it comes from, but I don't want to derive it 3 times in the same video, so I'm just going to write it down. dl turns out to be the square root of the quantity 1 plus the square of dy dx times dx. You see how one thing builds on another. This is why you don't want to just memorize things. You want to understand them so that you can reconstruct them whenever you need them. Anyway, what is all this junk? It's not just garbage on my scratch paper. I've told you what it is. It's important to write good notes for yourself too. The surface area of a typical infinitesimal slice is this stuff. Thus, the surface area of the entire surface of revolution is, how do we get it? We take the surface area of a typical infinitesimally thin conical frustum at x, let x take every possible value from a to b, and add all of those individual surface areas up, integrating, adding them up, starting when x is a, to get little frusta over here, all the way until x is b, which is where we stop. So we get area of a frustum, area of a frustum, area of a frustum, chop, 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 add, all the way, stop there. And that expression gives us the surface area of the entire surface of revolution. So again, please do not memorize this thing. I promise you, there is not a mathematician on the planet who has this memorized. There's just no point. The only people who have this memorized are calculus students who don't quite know what they are doing. Don't be like them. Think your way through it. You want the surface area of a surface of revolution? You chop the generating curve into infinitely many infinitesimal bits. That's easy to understand. You revolve them around the axis. That gives you a bunch of conical frusta. That's easy to understand. You get the surface area for a typical conical frustum, which follows from this easy to remember formula, and then you integrate. That's it. That's what you remember. Not this gibberish. This is the kind of thing you reconstruct from comprehensible ideas when you need it. Okay, to show you what I mean, let's do a concrete example. Let's set up and compute an integral that represents the surface area of a sphere of radius r. Now, presumably, you are far enough in your studies that you already know the surface area of a sphere of radius r. That's an important formula, and it's an easy formula to remember because it's quite interesting. But whether you do or not, let's go ahead and do this, and we will reach a hopefully familiar expression at the end of our calculation. So to begin our solution, we want to put this in terms of the sort of problem we just solved in general, where we are revolving a curve around an axis to generate a surface of revolution. Well, that's no problem. We talked about this sort of thing when we did an arc length integral to come up with the circumference of a circle. We'll just take a circle of radius r centered at the origin and consider in particular the top half of the circle, which is the graph of y equals the square root of the quantity r squared minus x squared. And if we revolve that graph around the x-axis, of course, we generate a sphere of radius r. Okay, now how are we going to set up an integral for its surface area? Well, you know the drill. Think of this curve as being made up of infinitely many infinitesimally small straight line segments. Here's a typical one of length dl right above a typical value x. When I revolve the curve around the x-axis, each little infinitesimal line segment generates an infinitesimally thin conical frustum. We're going to analyze the frusta to figure out the lateral surface area of each one, and then when we have an expression for a typical one, we'll add them all up with an integral. And that's that. Okay, our course is set, so let's start writing it down. We chop the surface into infinitesimally thin conical frusta, as in the figure. The lateral surface area of a typical frustum at x is, well, let's think our way through. It's a conical frustum. How do you find the lateral surface area of that? Oh yeah, there's that neat formula. You just multiply the length of its generator by the distance that the generator travels on that circle. So in this case, a typical frustum is going to have lateral surface area. Well, let's see. I'm going to start with the distance traveled by the midpoint. That way I'll get the length of the generator, which is where I'll get my dl or dx at the end, where it ought to be. So I need to think about the distance traveled by the midpoint of that little tiny infinitesimal generator. Well, that point is traveling on a circle, not the given circle. It's traveling on a circle that is sticking out in this extra dimension coming towards you out of the page. But at any rate, the distance it travels is the circumference of that circle. So it's going to be 2 pi times the radius of that circle that it's traveling on. Well, what's the radius of the circle it's traveling on? Hopefully you see that right away. But if you don't, it'll probably be easier to see if I redraw that frustum a little larger. Here's the frustum. Now it's traveling on a circle like this, that little green circle I've drawn in there. The radius of that circle is clearly the distance from this x up to this midpoint of the generator. And that's lying on this blue segment, which is part of the curve. So it's just the value of this function, this blue function at x. In other words, that distance is square root of r squared minus x squared, because that is the function I'm dealing with. So coming back to this, the distance traveled by the generator's midpoint, well, it's traveling on a circle, so its distance occurs on the circumference of a circle. So 2 pi times the radius of that circle, which we're looking at it here, is going to be square root of r squared minus x squared. Good. That's this piece. But to get the surface area of this frustum, I have to multiply this distance traveled by the generator's midpoint by the length of the generator, which of course is dl. Now dl, you should be able to explain using that differential triangle, has a nicer form that is going to be good for us if we want to ultimately integrate with respect to x. I'm not going to rederive it for a third time here, so I will just write it down all at once. It's the square root of 1 plus the square of dy dx times dx. Okay, so don't get lost. What is all this junk? This is a representation of the lateral surface area of a typical frustum at x. Now we want to simplify this if we can, but above all, we need to actually put in an expression here for dy dx. For that, of course, we do need to take this derivative, which we did in an earlier problem, so I'm just going to record that result right here. And when we substitute that stuff in for dy dx, we get all this stuff. Once again, the stuff under this radical simplifies to r over the square root of the quantity r squared minus x squared. Hey, look how nice that is. Now I've got a square root of r squared minus x squared downstairs and upstairs, so they cancel out, leaving us with 2 pi r dx. Great. What is this thing? We haven't forgotten because we've written everything down. This is the lateral surface area of a typical frustum at x. So this is precisely the thing we want to integrate. Thus, the sphere's surface area is, well, we're going to take our expression for one slice of area, but add all of the slices up, integrating as x goes from where to where. Well, we could start here at minus r, chop, 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 and stop at r, like so. that would do nicely. And sometimes students will say, well, wait, don't you have to double that? No, you don't, because at every value of x from minus r to r, we are getting the entire conical frustum. So you add those all up and you get the entire sphere's surface area. But we could make this a little nicer if we wanted to. Instead of going from minus r to r, we could just go from 0 to r, starting here, chop, 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 add, and we would get the hemisphere, but that would only give us half the sphere, so we would need to double at the end. So this is probably the nicest expression we could start with. It's always nice to have your integral starting at 0 when you can, because it's easy to evaluate at the end usually. Anyway, let's evaluate this thing. Notice something very interesting. We're doing an integral with respect to x, but our integrand is a constant, 2 pi r. R is just a constant in this case. So the whole 2 pi r can be pulled through the integral to give us 4 pi r times the integral of dx from 0 to r, or rather the integral of the function 1, the constant function 1. And if you integrate the constant function 1 from 0 to r, what do you get? I mean, you could do this by noting that the antiderivative of 1 with respect to x is x, and then use the fundamental theorem of calculus, which will tell you that the value of that integral is r, and that's fine. But integrals like this, just think about what it means geometrically. You're integrating the constant function 1 from 0 to r. So you are getting the area under the curve, which is just the area of that rectangle, and r by 1 rectangle, which is of course going to be r. But in polite society, we do not write r times r, we write r squared. And lo and behold, we have recovered the famous formula. The surface area of the sphere of radius r is 4 pi r squared. Now I said earlier, that's a very famous result that you should know. Hopefully you know it already, and one that is really easy to remember because it's interesting. Think about what it's telling you. We've got a sphere of radius r. Its surface area, according to this, is exactly 4 times pi r squared. But what is pi r squared? Well, that's the area of a circle of radius r. Everybody knows that. In particular, if we look at any great circle on this sphere, like this one, say the equatorial circle, the area of that circle is pi r squared. So that means on the whole sphere, we have a surface area that is exactly, not just close, but exactly quadruple the area of that equatorial circle. Weird. It's as if you could take 4 copies of that circle and somehow lay them out over the sphere and fit it perfectly. A very memorable result, and you have now just seen one proof of it. And now you know how to compute surfaces of revolution. You'll get to do it a few more times for homework, and remember to think your way through the problems carefully. You will thank yourself later, especially if your teacher decides to be sneaky and gives you exam problems that do not quite fit the usual formulas, but which are easy to figure out if you understand what you are doing and think through that process as you do it. It is also always a good idea in writing up your solutions to actually try to write up a coherent solution. Sometimes just a few little phrases will make everything clear, whereas just a jumble of symbols is unreadable. But enough of that. Go forth and integrate.